Hi everybody. So my name is Artur Kuzin, and today I will talk about Kaggle Open Images. That's actually not one competition, but three competition on the same dataset. And I was able to get free solid gold medal during all this free competition. So before we can start, please raise your hand who participate in this competition. One of them. Any? No? Okay. Please raise your hand who familiar with object detection or maybe segmentation approach. Oh yeah, nice. So, well, today we'll discuss some details, but not much. And yes, it's quite good that you're familiar with these tasks. So, free competition, one dataset. So the all free task is presented on this slide. So on the first competition, you need to detect the objects on the images, like in the center of the image. On the second competition, it's segmentation. And I would like to focus your attention that in some cases, instance can be split by several parts. For example, this person, it's obviously the one person, but it's split with guitar to two parts. It's separately, but it's one instance. And on the third competition, you need to make prediction about some kind of visual relationship between these objects. So, for example, man holds guitar, man on chair, and it's about property of the objects like wooden and other material and stuff. Okay, so but it's not the flattened structure of the classes. It's some kind of hierarchy. So, for instance, there is a torch, and in the same time, it's a flashlight. So you need to, for this kind of image, you need to predict two very identical bounding boxes, but with different classes. It's a little bit confusing. To more details, please visit the site of the competition. It's have very detailed description of this hierarchy. So I use only the first level of hierarchy, so it's a final leaf. And using this hierarchy, I can predict the other classes because, well, if I predict that there is a torch on the image, then I can figure out that it's also flashlight on the image. Okay, so about the data set. It was collected from the Flickr. So the organizer of this competition selects the images with CC BY license. That means that you can, using these pre-trained models, by training on these images in production. It's very important because, well, it's open images. Then they extract metadata, filter some memes, some ports, violence, and so on. Remove duplicates, validate the text, and make exhaustive manual annotation of labels and the bounding boxes. For more details, please read the paper about this data set. It's have very detailed description of this procedure. So when this procedure leads to bounding boxes, then they make some kind of automatically annotation with masks. So on the first stage, they train some segmentation model to make automatic annotation of the segmentation masks. And then humans annotator make some kind of interactive annotation using just click. So it's a positive click for the object and the negative click to background. After this procedure, they iteratively increase the quality of the segmentation model and make annotation for the rest of the data set. So the trained part was annotation some kind of semi-automatically, but the test part was annotation manually, using, for example, Paint or some kind of similar tools. So it's very important to know that train and the test part have some significantly biased in terms of annotation procedure. So this is an example from the article. They look very good because, well, there are some kind of difficulty objects with some kind of sharp structure. But if you look by yourself to the dataset, you can find some kind of these examples. So this is that's all annotation on the images. So you can find that shadows split object to the half on the left images. And there is some classes that corresponded to the mouth of the human and the humans itself. But on the right images, they annotate only one mouth. So I look like this grandma, then I look on this poor annotation. The second peculiar thing about this dataset is imbalance. This is very close to the real world problems, so it have huge imbalance. I would like to focus your attention that on the y-axis it's logarithmic scale for the object amount and for the class distribution. So it's very huge imbalance in the classes. So for example, some images like human was very common in this dataset, and some other images present only a few samples in this dataset. And all teams have to handle this imbalance in some kind of manner. So next is the metrics. It's also very important. It was mean average precision. So the first thing you need to know about these metrics is work this all range of the prediction from very little amount of score of confidence to the large one. So on the left images, it's only a few bounded boxes, but it's very, I don't know, very, it have most sense because it's about humans, tables, laptops. So if one can see these images, they have not complaints about the quality of this model, but it have only 0.03 score on the leaderboard. In the other hand, the models that have much significantly score on the leaderboard have a lot of bounded boxes with very little confidence and confidence of the object. But due to the metric, it's have more score on the leaderboard. The second part is about the stealth mode. So actually I achieve my very close to the best performance model in the middle of the competition, and I would like to not to show to other team my score. So this is the procedure. I just take the sample submission and my very best submission, split it in the half, and send separately these two parts to the leaderboard. So during this procedure, I was able to get to half of the scores. Then I make sum of these scores and have the assumption that I have this really high score on the leaderboard in the silent mode. But then I start submitting more and more samples. Then I found that this is not linear line on this slope. So the thing is, then I split my submission in the half and take the sample submission with zero prediction. Then I zero in the false positive detection, and it's make my score more higher. So I have more optimistic score on the leaderboard, in reality it's about 2% more less score than I expected. So it's it was very frustrating, but it's about the metrics. So you can't just split it in the half and check it on the leaderboard. Okay, so this is a quick overview of these tricks that all team from the top used to in their solution. The red one is the most important, in my opinion, and the bold shrift is some kind of tricks that I used to in my solution. For more details about for more details of these tricks, you can visit the site of Open Images, because all reports from the top team will be published on this site, I believe, during the week. So let's dive into solution. So the first part is filtering the data, because, well, I show that it have very noisy annotation with some kind of misleading of annotation. So I have two assumptions. The first one, if the sample have a lot of bounding boxes, that probably it's have a clear annotation. It's not true, but if you see that there is a lot of bounding boxes, then annotator make some kind of more attention and more time for annotate these samples. So if we just take some kind of threshold for count of object on the images, then and take more sample with more object than this threshold, it will be more clean than the whole data set. But you have in the same time some kind of imbalanced classes. So despite of the missing annotation, you really need to take all of the samples with very poor presented classes on the data set. So on the first approach, I just just take intersection of these two areas on the plot and train the first model on the very clean annotation. And then I just decrease the threshold for the objects on the sample and increase the amount of classes with very low presence. And I finished, well, I start from the 8 objects per sample and finish with 2 objects per sample. And for the distribution imbalance, I start from 800 classes and finish with 1000 classes. If I increase amount of the noisy data in the train set, that it's worsening my score on validation part. The second one is the dataset split. It was very clever, actually. So we have original train set. And after filtration, we have some kind of the clean part of this train set. To increase the amount of clean data, I just added to the train set part of the validation part. Because, well, during the description of this dataset, it was said that validation set have more clear annotation than train set. And obviously, if you just add some kind of clear annotation, it will increase your model performance. In the some extreme, I just leave about 300.5 samples for validation parts. And it was very actually stupid idea, because on this small amount of data, I was unable to check any of my hypotheses because it's very little amount of data to make some check with different approaches. And well, different check that I can make. Because of the metrics, it was very sensitive to the amount of data on your validation. So also I just implement implementation. So I used annotation framework, and for now it's implementation becomes standard parts of the pipeline for MM detection. So for the train procedure, I used this list of augmentation. It looks very strange to use, for example, random rotate of the images and gray annotation. But if you look carefully to the test sample, then they look something like this. So it's have upside down rotation. Obviously, some kind of foods and vegetables, it's not sensitive to the orientation at all. This is grayscale images of Philip Kirkorov, and the right part is from the gym, obviously, and it have a very large amount of noise and JPEG compression. So all this annotation, it's looks acceptable for this kind of test, in my perspective. About model selection. So I just, as I mentioned, I used annotation, and there are 2 ways to approach to this competition. You can start from the detection and then make the mask for the instant segmentation task. On the other hand, you can start from instant segmentation approach, and after that you can create bounding boxes using your masks. But if you look carefully to the same model with the same backbones, then you can find that multitask train with hybrid task cascade have significantly larger average precision for bounding boxes. So this multitask approach, when you have the masks for your training procedure, it's allow you to achieve better performance for bounding boxes. So I just, well, it's for obvious. It was obvious for me that I can start from instance segmentation. Using this mask, I'm able to get better pre-trained models and then fine-tune it for the detection. So it was my main strategy for this competition. About mask RCNN, it was a lot of work that a lot of words you can find in the internet. So just quick overview of this architecture. So you have some kind of backbones. It's ResNet, ResNext, DenseNet, whatever. You just take the bottleneck from these backbones, and using feature pyramid network, you create multi-scale, thick pipe of the features. And then using a region proposal network, you have some kind of proposal for objects. And with bounding box head, you, based on this proposal, you make the regression for classes and for bounding box. And then using this prediction and feature pyramids that share between bounding box head and regression head, you add head for the mask. So it's kind of a decoder from UNet that make prediction for the mask. So the mask head share between all of these classes. For more details, please visit this post on the Medium. It's have more clear description for this architecture. So in terms of terminology from ML detection, backbones called, well, backbones because it have a lot of convolution inside of them. Feature pyramid network called neck for some reason, and the rest of the parts called head. For, well, it looks like head, neck, and backbones, obviously. So the RPN is RPN heads, classes head is class head, and so on. So to be honest, it must be like multi-head picture, but for simplicity, I just picture is like head, neck, and backbones. So the really important part of my solution was that I didn't use random utilization of the weights at all. So all my weights was pre-trained from some kind of previous part. So for example, you have to fine-tune your models from Coca to open images. In the standard way, you just throw away weights of the classes and make some kind of random utilization from scratch. But instead of this, I just extract tensor for these classes from the Coca, concatenate them several times, and then just slice them to the new amount of classes. It's allowed me to make more fast coverage because, well, weights already was pre-trained from previous task. But it's very naive approach, and the first place from visual relation track make more advanced technique. So you have some classes that corresponded directly. For example, cat in the Coca dataset looks like cat in the open images, obviously. But you have also some kind of not direct classes like human in the Coca, and you have more precise splitting of these classes in the open images. So human split in the girl, woman, boy, and man. And you just copy paste these weights from the human to the corresponding weights for the these four classes. And it's allow you to make even better coverage because you have pre-trained all of the model, and all of these pre-trained weights is relevant to your new classes. Next thing is the sampling. So everybody used some kind of class-aware sampling because you need to have you need to deal with this imbalance. So in this approach, on the first step, you just sample your first batch of the samples in this way that you have the full set of the classes, and then from this subset you sample your batch in the normal way. So this allows you to to feed your model with rare classes more frequently than the other classes. And also I used some kind of EOU balance sample for proposals. It was from Libra RCNN from this article. So it's also improve your performance because proposal selects more carefully than random. So here's my training procedure. I rebuild rate from Coca without any random initialization. On the first stage, I frozen backbone and train only head and neck because, well, actually haven't much GPUs, so I have to pretend some kind of technique to increase my speed of the training. So with freezing of backbones, I able to pre-train neck and the head very fast. So then I unfreezing consequently some group of convs from the backbones and train with unfrozen last group of cons and last two of group of cons. Then I unfreeze the full backbones except stem. The stem is just first convolution with max pooling. And in the final step, I freeze back my backbones and train neck and the head on the large batch. Because in my experiments, it was very important because of, I don't know actually why, but it was very important to use large batch for this task. And also, this is my ensemble technique. Actually, it's not mine. It was proposed by Miras Amir on the iMaterialist competition. So in this approach, you just take every augmentation or every checkpoint of your model like independent model. So in each step of this augmentation, you just split your model on some kind of parts. For example, from backbone, you have proposals on feature pyramids, and during the standard procedure, you just select very few of this proposal using NMS. But you can combine all of this proposal from every checkpoint and every augmentation step to make more carefully selection of this proposal. Then you just using this ensembling proposal to make feature pooling from every checkpoint. Once again, make prediction of the bounding boxes using several heads from every checkpoint. Once again, repeat NMS, and also make this some kind of a final mask prediction using the mask head of every checkpoint. So for more details, please visit the GitHub. It have code of this technique. And final post-processing looks like this. So due to the more large amount of classes, I increased the amount of bounding boxes per images, and I reduce my score because it was very sensitive to the metrics. Also, I switch NMS to the soft NMS, and during grid search on the validation set, I just find the best combination of EOU threshold and minimal score threshold for this soft NMS approach. So it all was about the segmentation task, and then I switched to the detection task. And as I plan, I have very good pre-trained model for the segmentation classes, and this class was subset of the detection classes. So I decide to split all set of the classes, first level of classes, to the three groups on the initial plan. So the first level was for detection of visual relationship track, because I plan to participate on this track, and it was very important to train the expert model for this subset of classes. Second group I plan to take from segmentation, and also I plan to just train the detection model for the rest of the classes that's not included in the segmentation task. And also for improving my performance on visual track, I plan to learn independent model for the second level of visual track. But when I think of that, I have a subset of segmentation classes that have low score on the detection based on my validation. So I train my detection model for these 60 classes with the worst performance on the validation track. But I find that it was very important to retrain your detection for the, well, detection part. I mean, if you just take bounding boxes from your segmentation prediction, then it's have much worse score on the leaderboard on the detection part. So if you just take your segmentation model, throw away the mask branch, and retrain the detection, it will significantly increase your score on the detection track. So my plan, my final plan, looks like this. So I remove all segmentation model with detection and have to retrain 6 model in the last 2 weeks. It was very hard, but I was in some miracle was able to do this because, well, I trained the expert model for every subset of these classes. And in every step, I just used weight rebuilding as I planned. So, for example, I have a full set of classes from the segmentation part, but I plan to just take 60 classes for the very little subset of these classes. So I just rebuild my final regression weights and classification weights for the new amount of classes, just copy-paste corresponding part of this fully connection layer. Well, actually, it was all of my approach. So I just repeat my approach from the segmentation parts and then make the ensembling using the same technique, but without the mask approach. But I also tried to this ensemble technique from Roman Solovyov. It's called weighted box fusion. So the idea was not to use non-maximum suppression for your bounding box prediction, but use all of the prediction from all models to reweight your final prediction. It works very well on my validation part, but I was unable to make the final prediction with this approach. It was very important because using this approach, you are able to make ensembling for the very different model. For example, you can train a very huge model for all classes, like did the organizer of this competition. And using this approach, you can ensemble this model with your expert models. So I believe that it was very important for the next year competition. So make notes about this technique. And finally, about visual relation track. So my approach was very simple, so I don't want to talk much about this. So this is the approach of first place from the visual relationship track. So let's say you have bound box prediction from object detection track. So you have bound box prediction for every object on your images. Then you extract some features like visual. It's well about the prediction of the classes from the object detection models. Special, it's about some kind of features from the bound boxes. For example, you can create features based on the special placement of these objects. For example, area ratio of this sorry, distance between these bound boxes, angles, areas, and so on. And also you have prediction from the classes. So after this, you just train the model on these features like GBM. So I just use light GBM for this approach. And if all of these features looks like some kind of pairs of visual pairs, then model said that it's present on your prediction. But some additional technique is for this kind of hard example. So in naive approach, the man for the like GBM models, it looks like man on the bicycle, but it's not. So to overcome this misprediction, they just train some kind of model to make correction of this prediction. So they just select these images on the external bounding boxes, then blank all but all these objects, and just make classification for these new images. And based on this prediction, they reweight the confidence for these pairs. Well, my final weights, final tricks that didn't work for some classes, for example, for grape, I find out that it have more high score for the validation set than, well, it have more high score for segmentation task than for detection. So I just take bounded boxes from the detection and replace these bounded boxes with circles. So because the grape is round and it's easy to replace bounded boxes with circles, but it didn't work. So I hope it will be help you to the next year competition. So I believe that's all. I do believe that it will be next year competition, but it's some kind of new constraint, for example, for speed, or maybe for I don't know, different constraint. So stay tuned, and also thank you for your attention. And I would like to answer to your questions.
You may ask questions both in English and Russian. Любые вопросы по докладу или не по докладу к Артуру. Уникальная возможность. Нет? Отлично.
Can you please go to the slide with the training stages? Yeah, What was the point of the full training except STEM? Just to get a sense what was happening.
It's kind of standard approach in the ML detection. They always don't train STEM because the first part of the convolution is very same for the all kind of task in the image classification detection.
Okay.
Есть ли еще вопросы?
Hi, my name is Ivan. Thank you for your interesting lecture. Maybe I'm not an expert. I just wonder, could you tell more about pooling you use? Like K-max pooling, just max pooling, different kinds of pooling.
Well, the standard technique in mask recognition is row line pooling. So we just select the some kind of area that corresponding to the object in the feature map and make pooling of this area to the heads. So it's not max pooling, it's row line pooling. It's well, some kind of special technique for this.
Okay, thanks.
Thank you, but I didn't realize your validation technique. You said you use only 3,000 for validation, but it was a bad idea because you could not test your hypothesis. But you stayed with it validation or you made something new?
Well, this validation I was used in the last part of the competition, but well, it was very the most important parts. But obviously, you can validate your hypothesis using leaderboards. It's not the best idea, but it's have more amount of the images than my validation set. So I validate my hypothesis on the leaderboards finally.
Okay, thank you.
Есть ли еще вопросы? У нас есть время для одного, может быть, двух. Нет? Все. Thank you so much.